pass it over to Kira, who's going to be introducing our speaker.
Thanks. Yeah, we're delighted to have Ruosong here to talk to us today. He's a fourth-year PhD student at Carnegie Mellon, advised by Professor Ruslan Salakhutdinov. Sorry if I pronounced that completely horribly. So Ruosong's done a lot of work on the theory and applications of modern machine learning, and in particular, his recent work has focused on the theoretical foundations of reinforcement learning and deep learning. Today, he's going to talk about reinforcement learning with General Value Function Approximation. So over to you.
Okay, yeah, thanks for the introduction. And yeah, today I'm going to talk about reinforcement learning is General Value Function Approximation, and in particular, like probably efficient algorithms that works with function classes that has bounded Eluder dimension. So this is joint work with my PhD advisor, Ruslan Salakhutdinov and Lin Yang from UCLA. Okay, so we all know that reinforcement learning is a paradigm to model sequential decision-making problems. And by combining like reinforcement learning algorithms with deep learning techniques, we have seen lots of impressive applications that are not achievable without using reinforcement learning. Okay, so in this talk, I'm going to focus on like the standard episodic Markov decision process framework. So in this framework, the agent interacts with the environment in an online manner by following a policy. So policy is a function that maps states to actions. And in each episode, the agent executes the policy for each steps. So the agent will receive some initial state S0, and depending on S0, the agent chooses some action A0 and receives a reward value R0 and transits to another state S1. Okay, and now depending on S1, the agent chooses another action, and depending on S1 and A1, the agent receives a new reward value R1 and transits to the next state S2. So each episode is finished after the agent finished all the 8 steps. Okay, and like in general, the goal here is to use samples to find the policy so that the cumulative value of using this policy starting from the initial state is maximized. Okay, so mathematically, we have the V function and the Q function. So for a given policy pi and state S, V pi OS is defined to be the expected cumulative reward the agent will receive by following policy pi and starting from state S. The Q pi OSA is defined to be the cumulative reward, expected cumulative reward the agent will receive by starting from state S, choosing action A, and then follows policy pi. And like the goal here is, as I said, use as few as possible number of samples to approximately maximize the cumulative reward, basically like V pi O S0. So if S0, like the initial state is stochastic, then like the goal is to maximize the expected expectation of V pi O S0. Okay, so this is kind of like the framework that we will focus on in this talk. And for the case of tabular RL, we now have a pretty good understanding. So the tabular case is a case where a number of states, number of actions, and the planning horizon are all assumed to be finite. And for this case, we now know the text time complexity is the number of states times the number of actions times poly h, where h is the number of time steps, over epsilon squared, where epsilon is the design accuracy. So the issue here is in practice, the number of states could be huge. Like for the game of Go, we know that can be solved by AlphaGo. The number of states could be larger than 3 to the 300. And for certain video games, the number of states could be even larger. Okay, so this means that in order to make this problem tractable, we need to exploit more structures of the underlying problem. So in practice, people combine reinforced learning with function approximation. So the general idea is let's assume we have a function class with bounded complexity. So it could be linear functions or kernels or neural networks. Okay, and we assume the problem can be approximated by this function class in some sense. Okay, so what do we mean by the approximated by the function class? Well, it could be value-based assumption where we assume the value functions or the few Q functions can be approximated by the function class, by functions in the function class, or it could be like policy-based assumption where we assume the ultimate policy is a graded policy with respect to functions in the function class. And in this paradigm, the desired reinforcement learning algorithm, its sample complexity should be polynomial in H. H is the number of time steps in 1 over the desired accuracy, and the complexity of the function class. So for example, for linear functions, like the sample complexity should be polynomial in the feature dimension, but we don't want algorithm whose sample complexity polynomially depends on number of states. As I said, number of states in practice could be huge. So before getting into this question for reinforced learning, maybe we can ask the same question for supervised learning. And basic learning theory shows that, for supervised learning, dereference is sufficient for finding actual output predictors, but just running empirical risk minimization. And here, D is the complex measure of the function class, so maybe VC dimensions. So for supervised learning, this is indeed achievable. So the question is for reinforced learning, can we do this? Okay. So in this talk, I will be focusing on value-based method. So basically, the case where we assume the value functions can be approximated by the given function class. Okay, so this talk will be on general function classes, but in order to talk about the general function approximation, it's kind of hard to avoid talking about the linear case. So what kinds of previous results, or what do we know about linear function approximation? So the first thing we need to talk about is what kinds of assumptions do we assume here? Okay, so in linear case, we usually assume there's a feature extractor which maps state and actions to d-dimensional feature vectors. And now the question is we need to assume something is linear, but which Q functions do we assume to be linear? Or equivalently, the question can be how strong do we assume the representation is? And historically, people have been making lots of different assumptions. And let me introduce 3 of them in in a increasing strong order. The first assumption I'm going to introduce here is the weakest one, and last assumption will be kind of the strongest one. Okay, and the first assumption is the linear Q-star assumption, also known as realizability, which says the optimal Q function is approximately linear. So we just say something about the optimal one. Okay, and this is kind of the weak assumption we can make if we want to use linear function approximation. And there's strong assumption complete assumption, which has for all linear functions after applying the Bellman operator, the resulting function is approximately linear. So the Bellman operator is defined below if you are not familiar with the context. Okay, so there's an even stronger assumption called closeness. So historically, people have been using the complete assumption in the context of batch reinforced learning, but people then realize maybe completeness is not really strong enough so that we can do probably efficient algorithms in the linear setting. So then people start to kind of make strong assumption called closeness assumption, which says for all functions, for all possible functions after applying the Bellman operator, the resulting function is approximately linear. So you can see these 3 assumptions. The first one is kind of weakest, and last one is kind of the strongest. And for us, for theoreticians, if we want to kind of have algorithms that requires minimum of assumptions, because kind of the more assumptions the algorithm requires, the less likely it can be applied on problems that we care about in practice. Okay, so this is kind of previous assumptions in the linear setting. Okay, and okay, so now let's talk about kind of previous results about linear function approximation.
Sorry, Ruosong, there was a question in the chat about whether or not you could differentiate between this completeness and closeness assumption. Are you going to spend some time on that, or?
Yeah, so you can see the definition here is for completeness, we just assume that for linear functions after applying the Bellman operator, the resulting function is linear. But for closeness, we assume that for any possible even nonlinear functions after applying the Bellman operator, the resulting function is approximately linear. So this is the difference between these 2 kind of assumptions. Okay. And okay, so let's continue. So basically, like there could be two different settings: the online setting and the generative model. So in the online setting, the agent just interacts with the environment to collect data, and in the generative model, we assume like there is an oracle, like the input is stationary pairs, and by querying specific stationary pairs, the agent will receive like the corresponding samples, basically the reward values and the corresponding transitions. Okay, so there are like these two different kinds of settings. And in the online setting, if we just assume realizability, then most algorithms require the dynamics to be nearly deterministic. So the first work on this is by Wen and Vanroy, where they focus on deterministic system. So basically, they show that for deterministic system, there's an algorithm that achieves polynomial sample complexity. And recently, we were extending this kind of algorithm to the setting where the transition is nearly deterministic. And we also assume there are gaps on values, meaning that for the optimal Q values, the best actions and the second best actions, their difference is lower bounded. So if you like kind of want to know more about these kind of works, I can provide you a link. But in the generative model, this kind of nearly deterministic transition assumption is no longer needed. So basically, we can show that if we just have the gap assumption, where we assume the optimal actions and second best action, there's like a lower bounded difference, then there's an algorithm that achieves polynomial sample complexity. And there's also a recent paper by Chava and I guess his student that shows that if we additionally assume that there's like core states, a set of core states, then we can also have algorithms with polynomial sample complexity. And like for the companion assumption, we now have some algorithms that are statistically efficient. So there's an algorithm called Olive by Microsoft Research Group, and also there's another recent paper by Stanford Group, which shows that under this kind of companion assumption, there are algorithms that achieves polynomial sample complexity. Okay, so but the issue is like these algorithms are computationally inefficient, meaning that like they require solving some hard optimization problems. And like more recent work also by the Stanford Group shows that under the additional assumption called explorability, then we can have a computationally efficient and statistically efficient algorithm. Okay, so in the generative model, if we assume the companion assumption, it is kind of a folklore that in the generative model, we can have algorithm with polynomial sample complexity. I will talk more about this part shortly. Okay, and under the closing assumption in the online setting, a recent work by Jin et al. Shows that there's an algorithm with polynomial sample complexity, and I think like she has also gave a talk in this seminar. And an earlier work by Yang and Wang shows that under the closing assumption in the generative model, there's like an algorithm that have like polynomial sample complexity. Okay, so these are kind of like previous works on linear function approximation. And kind of we can see that if we want to focus on the online setting, and if we want like both computationally efficient and statistically efficient algorithms without making further assumptions, the kind of like the closing assumption is only setting where we have desired algorithm, like kind of satisfying algorithm. Okay, so this is roughly kind of like the state of the art results about like linear function approximation. Okay, so right, so okay, so let me give you kind of like intuition about why these assumptions are needed. So maybe let's first focus on the generative model. Okay, so in this setting, there's like a kind of a simple algorithm. We just find a wall condition basis. Okay, so like I will talk more details about what's the definition. So basically, like suppose like now we have like a two-dimensional feature space. Okay, we try to find a set of bases such that they span the whole space, but also more importantly, they span the whole space by using some bounded coefficients. So basically, like the linear combination of these two gray points span the whole space, and also like I want to make sure that the linear coefficients are bounded. Okay, so after finding these bases, let's just do backups on these gray points to get values, backups to collect the values, And after having the values on these gray data points, the basis vectors, let's use linear regression to generalize the values to the whole feature space. Okay, so let's do this level by level from the last level to the first level. And for each level, let's find the well-conditioned basis, do backups, and linear regression. And after that, we basically have correct values for all data in the feature space. Okay, so this is kind of the rough idea of what the algorithm should be in a generative model, and this works under the completeness assumption. Okay, so in the honest setting, the we need to do something more adaptively. The reason is we can no longer directly find good basis. Now we need to do something to adaptively find good basis. And this is kind of like the reason why we need optimism. We want to make sure our estimated values is always larger than the true value. Okay, so there are kind of two solutions to kind of ensure optimism. Because if you just do some estimation, obviously it may not be always optimistic. So we need to do something else to make sure the optimism. Okay, so the first solution by Jin et al. Is to add projected bonus function to ensure optimism. But the issue here is by adding projected bonus function, we now have nonlinear Q functions because of the added projected bonus. So this is roughly the reason why closing assumption is needed in Jin et al.'s work. And another way is kind of we solve a global optimization problem with this kind of nested confidence region constraints, because we care about linear regression. So it's quadratic constraints. Okay, so if we do this, we just require the completeness assumption. But the issue here is to do this, we need to solve a non-convex optimization problem, which could be computationally inefficient. So this is a reason why this algorithm is computationally inefficient. Okay, so this is kind of intuition why these assumptions are needed for the case of linear functions. Okay. So now let's get started to this work. So in this work, we are going to focus on general function classes. And so what linear function approximation is good, but the issue is for linear function approximation, we need to construct feature extractors with sufficient representation power. Meaning I want to be able to see something like linear functions over the feature extractor, are able to represent some Q function, maybe the ordinal Q functions, or some other kind of more larger class of Q functions. So constructing the feature extractor itself could be a hard task. We may not be able to kind of construct these kind of feature extractors. So that's the reason we want to kind of extend our knowledge about reinforcement learning with function approximation. We want to work with more general function classes, maybe kernels or neural networks. Okay, so the general algorithmic framework that I will be focusing on in this talk is upper confidence bound based value iteration method. So algorithm is actually simple. So this is kind of the general algorithmic framework in the work of Jin et al. So there will be multiple episodes in this algorithm, and for each episode, let's first look at later time steps, and then go to first few time steps. Okay, and for each time step, we have a bunch of data. So the data will be standard pairs and reward values and the corresponding transitions. Okay, and now let's construct some labels. The label will just be the reward value plus the V function of the transited state. So the label is really applying the backup operator on the data point. Now we have some data, we have some label. Why don't we just run least squares to try to find a function in the function class? So this is kind of the next step we want to do. We find a function in the function class with minimum squared error on the data we have. Okay, and now let's construct our estimation of the Q functions. So there will be two parts in the estimated Q values. We first query the function that is returned by the least squares, and kind of this is the first part of the estimation. And then we will add some bonus function to make sure that we are always optimistic, meaning that the estimated Q values are always upper bounds of the optimum Q values. Okay, and like let's talk about how to define this bonus function shortly. But after having this Q function, we can now have like the V function, like just define it in the Euro way, and now we can just play greedy policy with respect to the Q function, because like we have a Q function now, we can just choosing actions greedily with respect to this Q function. Okay, so the central question now is like, how shall we design the bonus function so that the estimated Q values are always like are always larger than the ground truth, the optimum Q function. So this is kind of like the thing we want to work on here, kind of like constructing the bonus function. Okay, so the way we are going to define the bonus function is as follows. Okay, so now we have a bunch of data. We have a data set. This actually automatically defines a confidence region. Why? Because like we know that the optimal function should be close to the function returned by least squares in some distance. So here I measure the distance by kind of summing up the squared error of like kind of contributed by all data points in the data set. Okay, and I know that the ground truth should be close to the one returned by least square up to some radius beta. Okay, so basically like this is the whole function class, and we have like this blue region, which is kind of like the confidence region like we currently have. And now like we just define the bonus function to be okay. So now we have a data point z. It is a state action pair. We just define the bonus function to be the difference between the largest possible value for fz minus the like smallest possible value for fc. Okay, so basically it's like the largest possible difference between functions in the confidence region applied on this specific data point. Okay, so basically like it is just like the largest possible fc minus f prime z, where both f and f prime come from this confidence region.
So wait a second, I'm sort of lost as to what z is here.
Oh, Z is like a state action pair.
Right.
Yeah, so because like here like we want to define bonus functions for state pairs, and z is just like kind of a shorthand for essays.
Right. Okay. Got it. Very good. Thank you.
Okay. Cool. So right. So this is clearly upper bound on the kind of confidence interval we have, and okay. So we can see that for the class of linear functions, this recovers the Euro definition of the squared bonus function, like the Euro square root of phi ZC inverse phi squared, like squared bonus function, quadratic bonus function. Okay, so so this is good. Like now we can make sure that everything is optimistic. But the question is like the first issue is like after adding this bonus function, the resulting function may not still live in the function class. Like maybe now we have like a function that lies outside the function class. Second issue is like for optimistic algorithms, we know that the regret bound is bounded by the summation of the bonus function. But what can we say about the summation of these bonus functions? And third issue is like the way the bonus function is defined is like we first calculate a confidence region, and the confidence region really depends on all the data we have seen. So this means like the bonus function itself also depends on the whole data set. And like the algorithm eventually, like if we run the algorithm for t episodes, there could be like t data points, and this means like there could be exponential in t different bonus function that we are considering, and that will cause some problem, as I will show shortly. Okay, so these are the three issues that kind of we want to resolve like in the later part of this talk. Okay, so any questions so far? Oh yeah, so like this Z is actually state and pairs. Like yeah, it's just a shorthand for essays. Yeah, sorry for the confusion.
Yeah. Right, very good. I guess the rest of the questions are resolved in the chat. So yeah, everything.
Oh, okay, yeah, okay, nice. Okay, thanks. All right, yeah, let's continue. So okay, so in order to kind of resolve the first two issues, we kind of want to make some assumptions. Okay, so the first assumption says like after applying the bonus function, the resulting function may not lies in the function class. So let's assume the function class has sufficient approximate representation power. Second issue is like we don't know how to give an upper bound of the summation of the bonus function. So let's assume the function class has bounded complexity. Okay, so now let's go to the two assumptions we are going to make to analyze the algorithm. The first assumption is, as I said, the function class should have bounded complexity so that we can make sure the summation of the bonus function can be upper bounded by something. Okay, to do this, we kind of make two assumptions. The first one is like the function class has bounded Eluder dimension. So I will talk about the definition, like about Eluder dimension shortly. But like the second assumption we are making is like the function class should have bounded log covering numbers, meaning that we can find a subset of the functions that approximates all functions in the function class pretty well. So like it's okay for the cover to have exponential size because here we only care about log covering numbers. Okay. So the second assumption we are going to make is like the function class should have sufficient approximation power. And so, as I said, like in order to have algorithms that are both statistically efficient and computationally efficient, like we must make kind of the closing assumption because this is the only assumption we now know to have such an algorithm even for the linear case. Okay, so this is going to be the assumption we require, like on the representation power or the approximation power of the function class, that for any function, we assume that after applying the Bellman backup operator, the resulting function should be is approximately in the function class, that can be approximated by functions in the function class. Okay, so the second assumption is used to deal with the fact that after adding the bonus function, the resulting function may not lie in the function class. Okay, as a reminder, this is definition of the Bellman backup operator, but I don't think it's kind of interesting, for the definitions here. Okay, so these are the two assumptions we are going to make to analyze the algorithm. And okay, so what's the definition of Eluder dimension? Okay, Eluder dimension is it was first introduced by Ruosong and Wang to characterize the complexity of bandits problems with general function approximation. Okay, so introduce the concept of Eluder dimension, like a very important concept is like absolute dependency. So let's assume we have a data set and another state and pair. We say this actual state and pair is dependent on this data set if for all pairs of functions such that the square difference between f and f prime on this data set, suppose that is sufficiently small, then this should imply that the square difference between these pairs of functions is also small on this actual data set. So intuitively, this says something like, for those functions that are close with respect to this data set, this should also be close with respect to this extra data point. Okay, so this distance is the kind of the summation of the square distance over all the data points in the data set. Okay, so this is kind of like the definition of absolute dependency. And okay, yeah, I saw kind of question like yeah, so Z1, Z2, this is 5. This is just kind of the data set. So Z is a data set consisted of these data points, and there's an extra data point Z, and we want to define when they is dependent on this data set, which is consisted of Z1, Z2, Z3, Z4, Z5. Okay, So, this is kind of definition of epsilon dependency. And definition of Eluder dimension is just kind of like, the longest sequence of data points such that each data point is not dependent on all previous data points. Okay, so for example, for these 5 data points, I want to make sure that Z2 is not dependent on Z1, Z3 is not dependent on Z1, Z2, Z4 is not dependent on Z1, Z2, Z3, and so on. So basically, like the Eluder dimension is the longest possible such sequence of data points. Okay, so this is kind of the definition of Eluder dimension. And now the question is like, why should we care about this? Okay, so we should care about this for 2 reasons. First, like for lots of examples, lots of function classes that we care about, their Eluder dimension can be upper bounded. So for example, for linear functions and linear functions, we can show that their Eluder dimension is approximately linear in the feature dimension. So basically, like if you use a feature extractor with feature dimension d, then the Eluder dimension is roughly d, up to some like log factors. And this can be extended to degree p polynomials. So if like we have like degree p polynomials, then the Eluder dimension will be roughly d to the pth power. And another very nice property about Eluder dimension is like if we want to remove some functions from the function class, then the resulting Eluder dimension will only be lower. So this means that Eluder dimension is really monotone, like in some sense. Okay, so actually combining the second property with the third property, we can kind of give bounds for some interesting function classes. So for example, let's consider a neural network with d-dimensional input, and a 2-layer neural network input like is d-dimensional, and the activation function is quadratic. Okay, and in that case, we can actually see that such neural networks will be subclasses of degree 2 polynomials. And as I said, like removing functions will only result in lower Eluder dimension. So this really shows that for neural networks with 2 layers and quadratic activation function, its Eluder dimension is upper bounded by d squared. Okay, so for lots of interesting function classes, we can upper bound the Eluder dimension. And another nice thing about Eluder dimension is like it can solve the second issue we want to resolve. Basically, like a very important technical lemma in like the work of Russo and Wang, which I think this is basically like a generalization of the elliptical potential lemma in the case of linear functions. They show that the summation of the bonus functions can be upper bounded in terms of the Eluder dimension. So basically, actually just shows that the summation of the bonus function can be upper bounded by the Eluder dimension plus square root of the radius of the confidence region times the Eluder dimension times the number of time steps, the number of episodes we have already seen. Okay, so recall that this beta is kind of the radius of the confidence region we are working on. Okay, so this is kind of nice because like this automatically resolves the second issue. Like now we know that the summation of the bonus function can be upper bounded. Okay, cool. So yeah, this is kind of the definition of Eluder dimension, and why should we care about that? Okay, so now let's go to the last issue. So recall that the last issue is that the complexity of the bonus function could be high. But why is that happening? So why don't we want bonus function with high complexity? Okay, so recall that we have a confidence region, and how is this confidence region defined? Okay, so we have the least square solution, which is FOLS. The confidence region is defined to be all functions which has sufficient small difference with the function returned by least squares. So kind of this is kind of the way the confidence region is defined. And this beta characterizes the radius of the confidence region. And as I said, like kind of the summation of the bonus function depends on this beta. And also because like summation of the bonus function is roughly like the regret bound we can get. So in order to kind of get a finite regret bound, we need to make sure we can have like kind of a finite beta so that this confidence region is valid. But now the question is like how large this radius beta could be. Okay, so if we can, to do this, we need to understand how well the Q values we estimated in level H concentrates around TQH plus 1. So QH plus 1 is the Q function we estimated for level H plus 1, and T is like the Bellman backup operator. So if we can show that QH concentrates well around TQH plus 1, then we can have some finite bound on this beta. Okay, and okay, so this concentration is a little bit tricky to achieve. Let's go back to the algorithm to see why it is the case. Recall that in the algorithm, we have a bunch of data. These are state and pairs with the associated reward values and also transitions. And the labels is defined to be the reward value plus the V value of the transition state, basically. Okay, so you can see that here, the data and labels are highly correlated with each other. Why? Because the way we collect data is by looking at all the previous data we have seen, and also the way we define the V function is always by like kind of look at previous data points and kind of get the V function. So basically like both the data and the labels, they depend on all the data we have seen. But on the other hand, we can apply concentration bound only if these labels are independent with the data. So if this V function is fixed in advance and they are kind of independent of the samples we collect, then we can apply some concentration bounds. Okay, so this is kind of like the issue. And actually, this kind of issue already occurs in the case of linear functions. Okay, so what are the ideas in the work of So basically, like their idea is to establish a uniform convergence over all possible V functions. For the case of linear functions, the complexity of the V functions is kind of okay. Why? Because the V function, we know it is just like max over all possible actions of the Q functions, and the Q function has a kind of a simple form. It is like a linear function plus a quadratic bonus function. So now we just need to understand the complexity of the Q function to understand the complexity of the V function. Okay, so what is the complexity of the Q function? Basically, like how many different Q functions could there be? Well, for the linear case, because of this nice form, like we can establish a easy current argument for kind of these kind of Q functions. Because the linear part, the complexity we know is roughly D, and for the quadratic part, we just need to kind of do a current argument over the covariance matrix in the middle, but we know that the covariance matrix, the complexity is D squared. So basically, like the complexity of the V function and the Q function, both of them is roughly D squared. Okay, so this argument is kind of nice in the linear case, but the issue is like for general functions, how shall we kind of do a such simple counter argument? Because like we no longer have such a nice closed form formula for the bonus function. So how shall I do this? Okay, so now the issue is like for our case, the bonus function could have a high complexity. So why don't we kind of reduce its complexity? Okay, so so our idea is to subsample the data set so that so there we want to achieve two goals. First one is like we want to make sure the confidence region is approximately preserved. Like we don't need like the confidence region to be super accurate, because like if we just increase this beta by a constant factor, it just increases the total required bound constant factor. So it doesn't really doesn't really matter. Okay, and like the second thing we want to make sure is like the total number of data points is upper bounded, so that like kind of the possible number of bonus function is bounded. So like the complexity of the bonus function is low. Okay, so this is kind of like the high-level idea of doing subsampling, but let's first apply this for the case of linear functions. Okay, so for the functions, sample the data set so that we can achieve both goals. Let's recall that the confidence region is defined to be all the d-dimensional vectors such that the squared L2 norm of phi times the difference between this linear function and the linear function predicted by these squares is bounded by some radius beta. Okay, so this phi is a data matrix. Each row is a feature vector we have. Okay, so basically, like we want to, the confidence region is something like this data matrix times the difference between the linear function and the one returned by the squares is, the L2 norm is alpha bounded. Okay, so for the linear case, how shall we subsample the data matrix so that this squared L2 norm can be approximated well? And kind of uniform simple. The reason is like, suppose like we have a data matrix, there are like n rows. The first, one of the row is non-zero and all other rows are simply zeros. Okay, so in order to approximate this confidence region, we should be able to find the row with non-zero entries. But how many samples do we need if we want to kind of do uniform sampling? Like we can show that if you do like, unless you do like, basically n samples, if the size of data set is n, otherwise you will miss kind of like the non-zero data point with high probability. Okay, so basically this shows that like even for very simple cases, uniform sampling simply won't work. And actually, this kind of guarantees that we want to achieve like subsample the data matrix to preserve the L2 norms. This is a well-studied problem in the community theoretical computer science. And why the is like it has like deep connection with like concept of spectral specifier, which is important when constructing like things like Laplacian system solvers and fast algorithm for solving min cut. Okay, and by now we have a pretty understanding about this problem, and kind of like we know that we can achieve a linear in the feature dimension sample complexity by applying importance sampling according to the so-called Larry score. So I won't talk about like kind of the definition of Larry score, but just to make sure like that there's a way to subsample the data set so that we can approximate the confidence region where we only need d data points, roughly d data points. Okay, so now at least we have an argument that works for the linear setting, and it could be possible to be generalized to the general function classes because like subsampling we can apply this in general. Like this is not something that is special about the linear case. Okay, so what we are going to do is to apply the so-called sensitivity sampling framework. So so let me first state the sample complexity we can get. The sample complexity we can get is roughly the Eluder dimension of the function class times log current numbers of the function class. Okay, so what will be the sensitivity sampling? It is just important sampling according to this kind of sensitivity, which is defined as follows. So let's interpret this in an intuitive manner. So what this is talking about, it's just kind of trying to measure the importance of a certain pair with respect to the whole data set. Okay, so basically like I'm trying to see what's the ratio between the squared error contributed by this specific data point and that of the whole data set. But the thing is like I don't know which pairs of functions are. Let's consider those pairs of functions. Basically like I do a maximization of all possible pairs of functions. I'm just returning the largest value between the squared error contributed by this specific station pair and the whole data set. Okay, so this is kind of the definition of sensitivity, but why this will work. Okay, so to give you some intuition, let's consider a much easier problem. Let's say like we have n real numbers, and we want to approximate their summation up to a constant vector. Okay, so as I said, like uniform sampling simply won't work. because like, suppose one of them is non-zero and all other, elements are simply zeros. In order to find the non-zero one, you need to kind of do like omega n samples, which is really bad. Okay, but suppose we have some prior knowledge about the numbers. So let's say like, we know the ratio between the S element and the summation is upper bounded by something bi, and we know bi. Okay, so this is kind of a prior knowledge about the largest possible fraction or contribution this element could make to the summation. Okay, so suppose we know such a upper bound. And if we know this, we can just sample each element with property bi. And it can be shown that, this one, returns a constant factor approximation with good probability. And on the other hand, the sample complexity of this algorithm is simply the summation of bi. So if we can find some good upper bound, then some complexity can be, significantly reduced.
So Ruosong, a quick clarification question. So the second bullet says, if we know that AI divided by sum of AI, but that's sum of AJ, and the sum runs from 1 to I, or?
Oh, this is just like summation from A1 to AN, like all the numbers.
All of them?
A1.
Okay, so that's just a normalization, so these are non-negative numbers, or something like that?
And like, this is kind of something between 0 and 1. So, this sample probability will always, bounded between 0 and 1 if you kind of, the perfect ratio.
Okay. Right.
Okay.
Yeah, fine.
Okay, cool. So, this is kind of like, the definition of sensitive sampling. We are just considering the ratio between the error contributed by this specific same pair and that of the whole data set. And of course, like, we don't know the pair of functions we are working on. So let's consider the worst case scenario. Let's consider the case where like the ratio is maximized. So this is kind of the, kind of the reason why we find sensitivity in this manner. And now the question is like, how large could the summation of the sensitivity be? Because as we can see here, the sample complexity really depends on the summation of the sensitivity score. And kind of like, something we can show that is a bit like surprising even to me is like the sum of the sensitivity can be upper bounded by the Eluder dimension of the function class, so that if you apply this kind of sensitivity sampling approach, the number of data points you will get is upper bounded by the Eluder dimension of the function class. Okay, so this shows that really after doing this sensitivity sampling, the number of data points can be controlled in terms of the Eluder dimension of the function class. Okay, so
yeah, so this does make some sense, because when you're bounding the regret, then you're bounding similar terms. But it's very interesting. So the question I had is whether this analysis is restricted to finite state action spaces, or does it apply generally?
Yeah, it can be like, applied, because like, so the scenario we are going to use is sensitivity is like after collecting a bunch of data, we are going to select a few of them to kind of approximate the confidence region. So we are always working on the case where kind of we have finite sample.
But this lemma itself.
It works for pretty generally, like just that like it doesn't really matter if the state space is continuous or whatever. Just requires like the function class we are considering to have bounded Eluder dimension.
Okay. All right.
Okay, so let's put everything together, and the final algorithm is pretty similar to the previous one. And kind of the only modification we are doing is like the way we define the bonus function. Okay, so we have collected a bunch of data. Let's do sensitivity sampling to reduce the size of the data set while approximately preserving the confidence region. Okay, so we have all the state pattern pairs, and we do sensitivity sampling. And now we can just define the confidence region in terms of this subsample data set. And then we can just use like the previous definition of the bonus function. Basically like, the largest possible difference of function values on this specific station pair, but we care about functions coming from this approximate confidence region. Okay. And the nice thing about this new algorithm is like now we can see something like the bonus function is complexity is bounded, because now the number of subsample data set is bounded. So the total number of possible bonus function is bounded. And kind of like, combining all these ideas about like Eluder dimension, kind of like closeness assumption, we can show that under the closeness assumption, this algorithm achieves a regret bound of Rudy times something like poly H, Eluder dimension, and log current numbers. So like, I promise like the degree won't actually be that like, big. It's something like 4 for the case of linear functions. So it's not that kind of bad, like, high degree polynomials. It won't be the case. Okay, so this is kind of the main theoretical result we have. And maybe let me conclude this talk by kind of summarizing, the algorithm and also kind of giving some future directions. So basically, like, we give a probably efficient algorithm by, kind of with like that works with general value function approximations. The complexity depends on the Eluder dimension of the function class and like the log current numbers, and it works under the closeness assumption, like as in a case that for like linear MDPs. And I think the main technical idea in this work is like we show that we can actually reduce the complexity of the bonus function by applying sensitivity sampling to reduce the size of the data set, so that the bonus function, it only have like bounded number of possibilities. Okay, and let me list a few future directions. The first one is like, can we get some algorithm with better computational complexity? Okay, so in this algorithm, we kind of want to sample this data set for t times. So suppose like there are t episodes. Each time we need to resubsample the data set, and to resubsample the data set, we need to recalculate the important sampling ratios. So this means that the time complexity will be at least t squared, which is kind of bad. So the idea here is like maybe we can apply some online sampling techniques. So instead of like resample everything again, why won't we just do some online sampling techniques to kind of reduce the computation complexity? Okay, and another kind of problem is like for the case of linear functions, our algorithm can actually achieve a regret bound of d cubed times poly h times t. This is because kind of like okay, so let me talk about reason later, but kind of our analysis only gives square root of d to the 4th times poly h times t. So there is like kind of Rudy factor. Okay, so why is that the case? Well, because like so the sample complexity of the sensitivity sampling part is the Eluder dimension times the log current numbers. For the case of linear functions, this is roughly d squared, because this part of the Eluder dimension is d, log current numbers is also d. So this is d squared, but we know that by a better analysis specific for the linear case, d samples is sufficient. So this means like maybe our analysis about sensitive sampling isn't really tight. Okay, so the question is like can we achieve a better analysis for sensitive sampling so that we can improve the regret bound of the algorithm? Okay, and kind of the third question is like, can we apply some of the algorithmic ideas in practical RL systems? For example, so if this kind of if it's possible to apply this kind of sensitivity sampling in practical systems, and of course, like as Euro, can we weaken the closing assumption? Like maybe we can get some both computationally efficient and statistically efficient algorithm that works under the realizability assumption, or maybe like complete assumption. So that would be like, I think, very cool directions for future work. And this finished my talk. Thanks again for coming.
All right, thank you very much. Let's give a little applause.
Oh, actually, I see a question, so maybe I can just answer that one. So yeah, so the question is like, algorithmically searching for f and prime for constructing the bonus is efficient? Yeah, this is a like very good question. Okay, so let's kind of go back to kind of the algorithm. So this is part of the algorithm where we need to search for f and f prime, but actually we can give another algorithm that can efficiently calculate this kind of sensitivity score by just kind of oracle access to the V's function. Kind of recall that the V's function is, where can I find definition for the V's function? Oh yeah, this bonus function. Kind of like, we need to kind of search for pairs of f in the function class to maximize this difference. So actually, to achieve this, to find like, the largest possible difference in the confidence region, people have already shown that this can be reduced to solve regression problems. So I guess, actually in Microsoft research, it has a paper on this, and Dylan Foster, I guess like SML last year, they also have like algorithm that reduces, this kind of calculating like largest possible difference to solving regression problems. And yeah, I think like in practice, assuming we have access to regression oracles won't be a kind of a strong assumption. Okay, so basically like, everything can be implemented if we have like access to regression oracles.
Right, great. Well, Sharon already took my question. That was my question that I was going to ask, and I was also going to point to this paper that you pointed to. So that's fantastic that you took care of this question. But so did you also try to analyze something like Thomson sampling for this setup? Because like the Russo and von Roy analysis also applies to that, not just this UCB style.
I guess like, even for the linear case, like, kind of doing Thomson sampling in the linear case, in the linear MTP setting, there are some technical difficulties, similar to this kind of, like kind of unicorn convergence issue. Kind of we want to.
Right.
Yeah.
Yeah, absolutely. Well, what I was thinking about was more of just a Bayesian analysis, right, where you don't have to care too much about this concentration. Really just bounding the Bayesian regret, or you just don't care.
Oh, but I guess still like, the dependency on data points will be the issue, right? Or yeah, like I should like think more about this, but like, yeah, personally, I haven't like kind of looking at these kind of problems.
Right. Well, the Bayesian analysis of Thomson sampling is like significantly simpler than the UCB analysis. Like you don't really have to show that your estimate is an upbounded value. So that just eliminates like half of these complications.
But does that require like a private knowledge of the like a private distribution, whatever?
Yeah, absolutely. So you're only gonna get a Bayesian type of a guarantee on the Bayesian expectation of the regret.
I see.
And still, there could be like a bunch more complications in this function approximation setting. So it's not fully clear how to pull it off.
I also do
right.
have a question. Can I? Is it
Go
okay
for it.
to ask?
Yeah, you can continue.
Okay. Yeah. So it's very interesting. I was wondering whether you actually do need to modify, you think, the algorithm. I understand that you do this for two reasons, for analysis and computation reasons, but like, would the original UCB algorithm be just fine? You just have to find some other ways of analyzing it, maybe along the ways that you were doing. So you could maybe just change the analysis of the standard UCB algorithm. Have you thought about this?
I thought about this, but I don't know. Kind of like, if we can do this, maybe we can just show like, Chi's algorithm achieves a regret bound of square root of d squared times t. Like if we don't want to go over these kind of covering arguments, right? But I don't think, kind of, that one achieves just d squared times t. I think kind of the, d to 3 halves is kind of necessary. So for that reason, I don't think we can avoid these kind of covering arguments. Because like, if you can kind of avoid this kind of covering arguments, like, the reason why, Chi's paper has like, d to 3 halves, two d's comes from like kind of the covering argument. And if you can totally avoid this, then you can improve the regret. But, personally, I don't believe that.
I guess we can say a possibility that we can apply NGR as an technique by like applying this, solving this the optimization problem. So in that sense,
kind of like the nested or kind of nested like constraints style or algorithm. But kind of the issue with that one is kind of the computation efficiency, and we really want some algorithm that is computationally efficient. Yeah.
Sure.
Hi. I had a query about the confidence bound. How do you manage the balance between the exploration and exploitation?
Oh, like basically, yeah. So basically, like yeah. So look at the way we are define the confidence region, and you can see that as we collect more data, this confidence region will be kind of smaller, because like after having more data, this actually like kind of stronger constraints than the case you have like only a few data points, because kind of this beta is not increasing. It's not like kind of increasing. So this means that after collecting more and more data, your confidence region will be much smaller. This means that the confidence interval will also be smaller, right?
So hello, this is Gugan here. Can you hear me?
Oh yeah, sure.
Yeah, so I had maybe a very naive question. So I wanted to understand, like broadly speaking, what is the advantage of using this general value function approximation? Okay, is it just that the problem of finding the right set of feature vectors where linear function approximation works well can be avoided? Is that the reason, or is there some more broader implications of working with general value function approximation?
Yeah. So the first motivation is like, for in order to apply linear functions, we need to say something like, by using this feature extractor, I will be able to represent some kind of Q functions, right? So this means that we need to kind of construct some super nice feature extractors. But how shall we even construct such feature extractor like this? That is kind of the first thing we want to understand. Second, kind of my personal take is like, eventually we want to understand like more complicated systems like deep Q networks. And for deep Q networks, we are not just like first train the representation and then train the linear part. Like we train them jointly, right? So kind of, this is kind of, beyond the linear case. And, that's the reason why, we should eventually understand the general case. We want to understand like, more complicated functional approximators like neural networks. That is my kind of personal take on this.
So I had a little question about the assumptions, right? So you had two assumptions. One was, well, that the function class is like sort of low complexity.
Yep.
But yet the second assumption is that, well, the function class is big enough, right?
Yep.
So these are conflicting in a certain sense. And can you like think of like problems that go beyond like linear MDPs where this would be satisfied? I'm just wondering.
I see. So like, in terms of like, specific examples, we can always construct some, but like, maybe we can think about like, generalized linear functions. Maybe, in this case, like, both things are just D, and this is still kind of a meaningful assumption, right? Basically, like we assume for every function after applying the Bellman operator, the resulting function is like a generalized linear function, like linear function apply a kind of like apply kind of a linking function.
Right. Yeah.
And also, so, like the kernel case, where like Eluder dimension is kind of like the effective dimension of the the kernel is still kind of like this is still a meaningful assumption, like this closeness assumption.
Yeah. I mean, I'm not really sure I buy that kernel example because like the Eluder dimension is like a worst case notion that has to apply for every sequence of data points, whereas the effective dimension is a data dependent quantity usually.
But like the effective dimension kind of you need to think about kind of the worst case like data sequences you see, right?
Oh my god. Okay. Well, that's gonna be pretty big. So, but here, when you show this assumption, you say that this needs to be approximately satisfied. So, do you actually have results for this approximate setting?
Yep, and like if this only approximate holds, then we have like a specification result, and just like there's like a linear term times kind of the approximation error of this function class.
And what is it multiplied by? Is it really just epsilon times t, or does it also have some dependence on the size of the function class?
Maybe also depends on the Eluder dimension. There are some multiplicative